Hey, Elizabeth. Hey, I just was thinking more through that Born-Haber cycle question. I know that you had asked for like a quick go-to method rather than having to do all these drawings for your exam. And I completely agree. And I totally was just empathizing with you that I think you deserve to have a quick method. As I was just going through my day, just thinking about it a little bit more, I was dissatisfied with how we left it for your sake, even for my sake. And I was like, you know what, there's an easier way. And I looked in my book a little bit and I said, there is a much easier way to handle these questions. So I'm going to try to just give you what I would say I think is your best go-to quick method to handle these questions. And I'm just going to pull up that same question that we were talking about with all the numbers. All right, so let me erase this part here. So how I would handle any of these Born-Haber cycle questions where you're relating lattice energy to delta H of formation. And then all the different subsequent steps. What I would start out by doing is just writing a simple equation on the board. Delta H of formation equals the sum of 5 steps. It's always going to, the delta H of formation is going to equal the sum of these 5 steps. Let me go ahead and explain why. Part of this is making sure that you have a good understanding of what delta H of formation means. Delta H of formation is the enthalpy change associated with forming a compound. That's why it's called with formation. Forming a compound from its elements in their standard states. So when this question, number 9.30, was given to you, that very last row was actually the standard enthalpy of formation, which you can kind of tell because it was written sodium solid plus 1/2 chlorine gas equals NaCl solid. So notice it's the equation of forming the compound NaCl solid from its 2 elements, the elemental form of sodium, both in their standard states, which is like the state that they're in at room temperature. So solid sodium and gaseous chlorine. So when they gave you that number, -411 kilojoules, what we both needed to see was that that was our left side. And by the way, I've totally changed my mind on whether you should approach it with this whole deal and all that. I don't think that's the best way, because I think it's too confusing with the signs and everything, with the lattice energy being presented in 2 different ways, with electron affinity, sometimes being negative, sometimes being positive. I think you should think of this as an algebraic equation. Standard enthalpy of formation goes on the left. Okay, so why are we equating it to these 5 steps? Okay, so obviously I said there's an equal sign, so we're equating it to everything on the left. Essentially what we're doing is saying, it's actually a Hess's law application. Hess's law basically says if you have a reaction, but you can think of it as really a series of steps, of like mini steps, then the sum of the steps equals the enthalpy of the reaction. So what we're doing here is mentally taking these 2 species, sodium solid and gaseous chlorine, and we're basically turning them into NaCl solid, but not all in one fell swoop. We're doing it through these mini steps. So in summary, the first 2 steps are essentially to get single gaseous atoms. We want single atoms, we want them gaseous. So if you look at the solid sodium, the very first step is almost always, because usually these are forming ionic compounds, so it's usually always a metal. The first step is to sublimate the solid, and that's where your 109 kilojoules value comes in. We are essentially turning the solid into a gas. So that's gets our sodium to be gaseous. The chlorine, it's not about being gaseous, it already is gaseous. It's about getting single atoms. So essentially we are going to be, for step 2, the whole point is just break that chlorine bond, and that gets you 2 chlorine atoms. Now here's where you have to multiply this one by 2, because you really, by 1/2, because you really only need half a mole, or half a one of these. Okay, so that's where you want to multiply that by 1/2. That gets you your chlorine atom gaseous. So those are the first 2 mental steps. Second, the third and the fourth step are all about taking those neutral atoms and making them ions. So you can think of the third step is being the ionization energy of the metal, and that is given to you as 496 kilojoules. Notice it really doesn't matter. I'm just pulling whatever signs are given. So I'm adding. So it's kind of simplifies things a little bit. You don't need these down and up arrows. You're just adding step 1, step 2, step 3, step 4, step 5. Step 4 is the electron affinity. It's essentially turning the chlorine atom into an ion by gaining an electron. And for this one, it's absolutely a negative number. But I want to just reiterate, sometimes electron affinity is a positive number. It doesn't matter. With this method, just throw it on in there. You're adding these all together. So just putting in this big sum of steps. And then the last step is your lattice energy. Now your lattice energy is the only unknown in this question. This question actually gave you the standard enthalpy formation. So this is the only unknown in the question. From what I can tell, usually these questions are either solve for this by being given this, or solve for this by being given this. If you're given the lattice energy in this type of question, what you're going to see is the lattice energy turns out to be a negative number. So that's the presentation of lattice energy as in being the energy associated with forming the lattice, bringing that cation and the anion together. That's going to be an exothermic process because you're going from unstable, where they're far apart, to stable, where they're together. So if you just throw this thing in your calculator, I'm just adding up these 4 steps, just simply adding them up. 109 plus 243, well, 243 divided by 2, plus 496, plus a negative. So you don't even have to think about up arrows, down arrows. Just add whatever it is. If it's exothermic, add a negative. I'm getting, just rewriting the equation, positive 377.5 kilojoules plus the delta H of lattice energy. And then if I'm solving for lattice energy, I'm just subtracting this from both sides. And when you do that, you will get negative 788.5 kilojoules, which is the correct answer for lattice energy, but I think your teacher is presenting them more from the opposite side of how much energy is required to break the bond. Just switch the sign. It's 788.5. But my point is that if on an exam, if you're given this type of question, and you follow this concept where you're setting the standard enthalpy of formation equal to the sum of these mini steps, consider that a negative number. Just like in the pictures that we saw on the slides, the lattice energy was always a down arrow. So it's presented as exothermic in the math calculation, even if you report the answer as endothermic from the point of view of how much energy it is to actually break the lattice, not form the lattice, okay? So I hope that made sense. I really think this is preferable than trying to draw the up and down arrows. It actually will always, you can always solve it like this. Standard enthalpy of formation on the left, okay? That's the overall reaction, and these are the steps that you can think of as basically being the same thing as the overall, because you started with the 2 reactants, and by the end you've joined them together. That's essentially what you've done with this overall reaction. I hope that helped. I hope it clarified. It did for me once I saw it as a math equation. I think it's much easier. Just add every number together and then just deal with the signs as they're given. The only other thing I would say is that just like you had to times this by 1/2, if there's, for instance, say it was MgCl2, if you had to ionize 2 chlorines to get your 2 anions, you would have to multiply that by 2, electron affinity, just to get the stoichiometry and like the numbers correct. So anyways, I hope it helped. It helped me to think about it like that way. And anyways, good luck, and just be in touch. Okay, bye-bye.